Okay, so we've reviewed Markov chains, and we're ready to talk about our first Markov chain Monte Carlo MCMC routine, and it's the Metropolis Hastings algorithm here. And I'm just going to go over this introduction to the Metropolis Hastings in this vignette, and you can look at more examples here. So the Metropolis Hastings, remember the key idea behind Markov chain Monte Carlo is to set up a Markov chain whose stationary distribution is the target distribution that you're trying to sample from. The target distribution might be a posterior distribution in a Bayesian inference problem, for example. So if you've done a course that involved Markov chains before, you may have had a different kind of exercise where you were given a transition matrix P. You were given the Markov chain's transition matrix P, and you were asked to find its stationary distribution. Find pi, so it's a pi p equals pi. And here you've got kind of the opposite problem. You're given pi, if you like, you're given the target distribution, you're given what you want the stationary distribution to be, pi, and you need to create a Markov chain that has that stationary distribution. So you need to kind of create P, or at least create a way of simulating the Markov chain with transition matrix P. So the Metropolis Hastings algorithm is a quite remarkable and very simple algorithm that does exactly that. Okay, so essentially the user supplies pi, the stationary distribution, and the Metropolis Hastings algorithm supplies P. Well, okay, actually you have to give the Metropolis Hastings algorithm a bit more to work with than just pi. What you have to be able to give it is a kernel, a transition kernel Q, and that kernel doesn't have to satisfy very many requirements, but it has to be irreducible. It has to be able to get all around the space eventually. So that Q kernel is called the proposal kernel, often for reasons that we'll find in a minute. But and usually it's pretty simple, the kernel. So Q could just be set. So Q is just a way of, given the current state, generate a new state. Well, at least a proposed new state. We'll see in a minute how this works. But let's, for now, just think of Q as whatever the current state is, I'm going to add a random number to it, maybe a random normal 0, 1 to it. That would be a proposal kernel Q. Okay, so let's have a look at the introduction maybe before I get ahead of myself. So here we go. This is it. As I've said already, maybe to implement the Metropolis Hastings algorithm, you have to provide this kernel Q, which is simply a way of moving around the space. And maybe I should say, I'm going to do an example in a minute. We're going to look at an example in a minute where we're trying to sample from an exponential distribution using Markov chain Monte Carlo. So it's not hard to sample from an exponential distribution, and an exponential distribution isn't really a very interesting, it's not a posterior distribution from an interesting and difficult problem. It's just an example to show you how MCMC works and how the Metropolis Hastings algorithm works. So for the moment, we're thinking about a one-dimensional continuous distribution. So our Markov chain is going to live on the real line, or actually on the positive real line, because the exponential distribution lives on the positive real line. So think of a Markov chain living on the real line, and so our Q has to be a way of moving around the real line. And as I've said, we can use this Q, which is just generate, if you're currently at X, add a normal 0, 1 to X, and that gives you a new value Y. So we could write the kernel explicitly in terms of the transition density, of the normal PDF probability density function. Okay. And so, there are other kinds of kernel people use when they're doing MCMC, but this kind of kernel is very common, and it's called a random walk kernel, where you're basically take the current state and change it a little bit by adding usually a normal, but sometimes some other distribution, random variable to it. Okay, so this is called a random walk kernel. And because of the role Q is going to play in our algorithm, it's often called a proposal distribution. And so this would be called a random walk proposal distribution. This is all going to become clearer when you see what the algorithm is. So here's the algorithm. It's very brief. So firstly, you have to initialize X. And the inputs to the algorithm are essentially a target distribution pi and a transition kernel Q. So you initialize X, and then you just repeat the following steps. You sample a Y from Q of Y given X. Okay. So you use Q basically to tell you for your given X1, what's the proposed value for X2. So think of this as a proposed value for X2. And then the next step of the algorithm is to either accept that proposal or to reject it. And if you reject it, you stay where you are, you don't move. So that's what the Markov chain is going to do. So A here stands for acceptance probability. So the A, because it's a probability, has to be no bigger than 1. So that's why this minimum of 1 and something comes in, because A has to be at most 1. So the really interesting part of A is this second term here, which, as you can see, is the ratio of pi computed at Y to pi computed at X times the ratio of Q xt given Y divided by Q of Y given xt. So we'll come back to this acceptance probability for a moment, in a moment, but to get some more intuition. But just notice that you only need to be able to compute pi and Q in order to compute this acceptance probability. And in fact, you don't even need to be able to compute pi and Q necessarily. You just need to be able to compute these ratios. And so that actually turns out to be key, because for pi, if pi is a posterior distribution from a Bayesian calculation, it's often actually hard to compute that posterior distribution exactly, but you can sometimes compute ratios of posterior distributions, because the posterior distribution is proportional to the prior times the likelihood. And so if you divide one posterior distribution by another, the constant of proportionality cancels out and you don't have to compute it, and that's the hard part. So we'll come back to that as well, but just to note, we don't actually have to be able to compute pi. We only have to be able to compute pi up to a constant of proportionality, because then we can compute these ratios in here. And for Bayesian calculations, that means we only have to be able to compute the prior and the likelihood, which we usually can. Not always, but usually can. Okay. So we compute A according to this rule, and then we toss a coin, and with probability A, we accept the proposed move, and we set the next state, xt plus 1 to be Y. Otherwise, we set xt plus 1 to be xt. That is, we reject the move and we stay where we are. It's really important to stay where you are and not just to keep going until you accept something and then update xt plus 1. It's really important to do this so xt plus 1 actually is equal to xt, because one of the ways that the Metropolis Hastings algorithm makes sure it has the right stationary distribution. Remember, the goal here is to have a Markov chain whose stationary distribution is pi. And one of the ways it does that is to stay where it is more often in places where pi is big. We'll see that again later. So, okay. So remember, the idea is that we need to try and create a Markov chain whose stationary distribution is pi, and actually this algorithm, this is all it is, that fulfills that as long as it satisfies certain regularity conditions. Like, you know, if Q just always stays where it is, that's not going to work. You need the proposal to be able to move around, but they're pretty minimal conditions. Okay, so to get a bit more intuition, it's actually helpful just to simplify a little bit and consider the special case where Q is symmetric. So that random walk proposal we just mentioned is symmetric, right? So Q of y given x is equal to Q of x given y for all x and y, because the probability of going to y if you start at x is equal to the probability of going to x if you start at y, because the normal distribution that we're adding to the current value is symmetric about 0, essentially. So, or you can just take a look at the mathematical form here and see that if you swap y and x, it doesn't change. Okay. So because of that, the ratio of the Q's in the acceptance probability for A, they cancel. Q of xt given y equals Q of y given xt, so those cancel, and the expression for A simplifies. So this special case where the Q is symmetric is called the Metropolis algorithm, because in 53, when they first proposed the algorithm, they assumed Q was symmetric and they had this cancellation. And it was later in the 1970s that Hastings presented the more general version that's now known as the Metropolis-Hastings, which allows Q to be asymmetric. So because of that, this ratio of Q's in the acceptance probability is sometimes called the Hastings ratio. So the Metropolis algorithm is just the case where Q is symmetric. The Metropolis-Hastings is the more general case where Q can be asymmetric. So let's look at the Metropolis algorithm for a moment. Just let's consider the special case where it's symmetric. What you can see is that the acceptance probability is going to be big if y has a high value of pi relative to the current value of pi, or at xt. So we tend to accept moves that are proposed where pi is big, and we tend to reject moves and stay where we are if we're proposing to reduce pi. So let's just look at why that might be sensible. So okay, this is an exponential distribution that we're trying to sample from. Okay, so what does it mean for the Markov chain to have this as its stationary distribution? It means that in the long term, the proportion of time it spends in any given location here is proportional, or well, equal to the area under the curve, right? So this is meant to be an exponential. Let's just e to the minus x. This is x. So that integrates to 1. And so what we want for our Markov chain is that the amount of time it spends in any given position on the x-axis or in any given region is proportional to the area under the curve. So in places where pi is big, like over here, we want it to spend more time there than in places where pi is small, like over here. Now, if you think about what our Q was doing, it was just a random walk. So it's not going to spend more time here than here, or here than here. It's going to kind of spend time all over the place. So it's this acceptance probability that kind of fixes up the proposal, so that the whole thing spends more time in places where pi is big and less time in places where pi is small. So let's just look at that. Let's suppose this is xt. If we propose to move this way to y, the acceptance probability there is going to be less than 1, because the acceptance probability is pi y over pi of xt, which is less than 1 for this example. It's not much less than 1, and that's because the pi's there are pretty similar. So you don't want to bias things too much. But on the other hand, if it proposes a move to this y, let's call it y, let's call that one y2 and y1, pi y2 over pi of xt, of course, is bigger than 1. And so, in fact, the acceptance probability will be 1, and you'll always accept moves that are going up in terms of pi. So because it always accepts moves that are up, but it sometimes rejects moves that are down, where up or down here means in terms of the value of pi at the current location, it will eventually spend more time where pi is big, or in the long run, it will spend more time where pi is big and less time where pi is small, which is exactly the qualitative behavior we want. And what's not clear, but is true, is that in fact, it's the amount of time it spends in any given part of the space is exactly proportional to pi. or more formally is the area under the curve of pi. So if you look at a small neighborhood here, epsilon, the amount of time it spends in any epsilon neighborhood will be proportional to the pi at that location. That's not obvious, that needs proving, and the the outline proof is on the dyno list. Okay. So yes, the proof is here about detailed balance. Go over that. So back to our example, let's have a quick look at the toy example. So our goal here is to sample from an exponential distribution. It's a toy goal. So here's the target distribution pi. And so I've coded up the target here. It's very simple. If x is less than 0, then the target is 0. Otherwise, it's the exponential of minus x. And then here's the code to implement the Metropolis Hastings algorithm. So this first line here, x, we're just initializing x. X is going to be storing where our Markov chain is. And x1 is just the first, where we start the Markov chain. So I'm going to start it. I just chose 3 as a starting point. You want to choose somewhere where pi is non-zero as a starting point, but we'll get, otherwise it doesn't really matter. And then this just iterates those steps, and I've tried to write this out so that it's as kind of clear as possible. So current x is where we are now. So xi minus 1, when the first time this goes through, I is 2. So the current x is x1, which is 3. That's right. And then the proposed x, we generate a proposed x by adding a random normal. There we go, a random normal to the current x. So that's like generating y, if you like. I call it proposed x here. And then we compute the acceptance probability as the ratio of the target evaluated at the proposed x divided by the target at the current x. So remember that Q's cancelling out here because it's this symmetric random walk. So we don't need to worry about the Q term. And we don't need to worry about the minimum of one and part either, because the way we decide whether to accept is just generate a random uniform number and look to see whether it's less than A. So we generate a random uniform on 0 to 1. This 1 here just means you just generate one of those random numbers. So it's a random number between 0 and 1. So what's the probability it's less than A? Well, it's A, right? It's the probability that a random uniform is less than a half is a half. The probability that it's less than a quarter is a quarter. The probability it's less than A is A. Well, as long as A is not bigger than 1. If A is bigger than 1, then the probability is 1. Okay. So in fact, the probability is a minimum of 1 and A. So essentially, this happens with probability minimum of 1 and A. And if that happens, we accept the proposed move. That's this xi here, is proposed x. Otherwise, we set xi to be the current x. That is, we quote, reject the move and stay where we are. And as I emphasized earlier, it's important that you actually do count that move. You don't just keep going until you propose and then store xi. You actually keep, I increases every iteration here, even if you stay where you are. Okay, so if we look at what happens when we, the x-axis here is the iteration, and the y-axis is just what's the current value of the Markov chain at that iteration. This is a continuous valued Markov chain, so it's living in the non-negative real lines, or the positive reals. And yeah, well, this is just this is sometimes called a trace of where x has gone. Can't see very much from that, but what you can see is it seems to spend most of its time near 0 rather than far from 0. And if we plot a histogram of the plots, you can actually see that a bit clearer. And the red line that's overlaid here is exactly the target distribution, the exponential distribution. So what you can see is that the Markov chain, the proportion of time it spends at any given location is proportional to the area under the exponential curve, right? And that's because the Markov chain has the exponential distribution as its stationary distribution, and it converges to that stationary distribution. So as long as we run it long enough, we expect to see this histogram. So we obviously did run it long enough here, at least, to get a pretty good visual appearance. So I'll just mention, if you go and look at the next vignette, you should play around with the code here and try some different things. So things you could try playing around with include what happens if you change the proposal from a normal with variance 1. So this Q, instead of adding a normal 0, 1, try adding a normal with a bigger variance or a smaller variance and see what happens. And it's important to note that, you know, changing the proposal in that way doesn't change the stationary distribution. It should still work. Everything should still work. But what you can find is that depending on choice of that proposal distribution, that Q, the Markov chain can converge faster or slower to its stationary distribution. So in other words, it can take longer. You may need, in some cases, you may need to run it for more than 10,000 iterations to get something that looks like this. So of course, it's a very simple example, and we'll do some more realistic examples later, but I hope this is a helpful introduction to the Metropolis Hastings algorithm.